Welcome to qnawire.
Moving on with some work related to our physical chemistry, so we're looking at more calculations again. In this first part A, we are taking a look at the ideal gas equation, which is PV equals nRT. And then what we're looking to solve is the density, so the second equation we need is density is equal to P over RT. So we can solve for the density of methane at negative 260 degrees Fahrenheit. At 1 atmosphere pressure is 0.110 pounds per foot cubed. And the density of methane at 80 degrees Fahrenheit or 540 if you want to convert it is equal to 0.041 pounds per foot cubed. So since the pressure is constant, the overall process and gas constant for the ideal gas equation will also be considered a constant in this case. So the densities of methane at different temperatures would also be considered quite accurate. And so the reason for the estimation of densities at different temperature So in the next part, we've got B and the volume of nitrogen. Which we consider Vn2 needed to displace methane, just CH4, will be approximately 28224 gallons. Then we can use our mole balance equation for the third part. That is N.ACC, accumulation is N output, subtract N add N gen, subtract N com. So we can solve for the volume of air required to increase the oxygen concentration. Is 2.24 times 10 to the 7 gallons. So next, because nitrogen, N2 gas, is at normal temperature and pressure, it is liquefied when it is compressed and then stored within a vessel. So when it comes at NTP, the gas will be vaporized due to its properties. So methane gas is purged with nitrogen first, but opposed to purging with the air because methane is heated to its service temperature at about 80 degrees Fahrenheit. So if methane is to be purged with air after being heated, it would have been easily combusted due to the presence of oxygen. So the logic for vaporization of nitrogen and reasons for purging with air we have just discussed.